For those of you guys joining us, they're in the back of their homework spiral attempting this AP-ish problem. Information given somewhat similarly than we've seen in the past, but information also a little bit unique. See the word Taylor pretty quickly, so we know to place it in chapter 10. See polynomials, that means we're not doing the infinite Taylor series, but rather the finite. Anyway, lots of hints. Calculator is permitted, but not necessary, at least not right away. Do you guys have your calculator out and calculator ready? Do you remember your Taylor polynomial formula? If not, you're looking at it. Are you enjoying your Friday? Are you ready to come have like a drive-in movie experience on the quad?
Drive-in?
Well, it's about the closest that we can get around here. Unless you do like the rooftop cinema, but even then you have to like wear those weird headphones.
A silent
disco.
That was fun.
Oh no.
I don't.
It's so funny walking in on people doing it.
Yeah, that's true. I know at grad night, I don't think they had it last year, I think it was 2 years ago. There was a whole section with like the silent. Oh my goodness. Dance party, what's it called? The dance floors. They set like different clubs around. Anyway.
Did we just stand there?
It was pretty funny. It was actually hilarious. Yeah.
Do you remember what people minus 2?
I do everything.
Not for yesterday.
Oh, did I not get it in there? That's fine. Okay. Sorry, kiddo. No one's being bad. Unless you are. Oh!
Despicable.
Teacher's lounge. Alright, I'm gonna start playing.
I'm really tempted to using
Oh, my nerd.
Do you guys do X and then do you plug in, or do you go straight to plugging in? I'll do X and then plug in. So we need my f of 2 plus f prime of 2 times
X minus 2.
x minus 2. And AJ, we keep going until we reach, what did they say?
Third degree.
So we're going until we reach,
Third degree.
oops, I just put the third because you said third. The third derivative, right? Did you guys remember your factorials, or did you forget? Did you remember your x minus 2, or did you forget? Are you blocking everyone's line of sight behind you? Or are you, oh, there you go. It's a Friday. We're supposed to be using it to approximate 2.3. So, question, where do I plug in?
6 plus 4 times.
X, I'm plugging in 2.3, but when I plug in 2.3, do you see how or why they centered it at 2? They're not that far off, yeah?
Yeah.
Okay, but yeah, you guys are plugging in, right? So you have 6 plus 4 times 0.3, true? Plus, because we just subtract the 2 minus 2.3. Why am I going to start simplifying? Why not just throw the mess in and box it and be done? I have to plug it in my calculator anyway.
Yeah.
As long as I'm super careful, it'll be okay. If I start not being super careful, I'm going to have some trouble. 2 factorial, yes, I can find it in my calculator, or I know it's 2 times 1 because I'm awesome like that, and I have 0.3, aren't you?
Wow. No.
And then plus, oh, come on, 8 over 3 factorial, that's just going to be 6, right? 3 times 2 times 1, or 2 times 3?
3 factorial.
And then I have 0.3. And now I'm throwing that puppy in my calculator because they said I could, because they said decimals.
Anything else?
And you guys can double check me, yeah? You're not just going to let me write down an answer and not be sure it's right. Did you? 6.921. Which is approximately f of 2.3, just showing them a full comprehension of what I've just done and what it means, yeah? So why the heck, if I'm doing a third degree Taylor polynomial, are they all of a sudden talking about a fourth derivative? And the maximum bound of a fourth. Lagrange. Oh, hey, they even say Lagrange.
Sorry.
Where does that name come from?
I don't know. I'm guessing it's French. Who is Lagrange?
You should ask Tony Lagrange.
Ask Tony. Does he have a good French accent?
Thomas is French.
Thomas is French.
Lacroix. Lacroix.
Woo!
LaCroix.
Well, reminds me of a lot of reading.
Like
Lagrange.
like you.
Okay. Figure out where he's from and what year he was born. Okay, so the fourth derivative of f satisfies the inequality. Sweet, I know the maximum of the fourth derivative and I'm gonna use it. Now, to find the Lagrange error bound for T3. I think, I haven't decided. David and I were talking yesterday. Mostly me, because he was asking about a Lagrange question.
He's a French, born in 1736.
1736, French. So we can say Lagrange.
French dude.
Okay. Oh my goodness. Okay. The question is whether we write down what we're actually doing, which is the third degree Taylor polynomial approximation of 2.3, and how far off it is from the function at 2.3. Taylor's theorem, which you guys can see in your book, you can read, you can look at, is talking about kind of like MVT. There is going to be a C within the interval from my center and my approximate, well, the x I'm using to approximate. There is going to be some C in between there where the actual error is equal to, this remainder. Some say that Taylor didn't really figure it out. It was Lagrange, so they named the remainder after Lagrange. That way he could be famous, even though the theorem was named after Taylor. Anyway, there was this whole debate. It might be in your book, or it might have been I found it somewhere else. But either way, so the hard part is Taylor's theorem says there is a place where the error is equal to, or the remainder is equal to, this expression. The problem is we don't know where that C is. So we say, let's think of blessings, an error bound by maximizing the fourth derivative, or the n plus first derivative. Let's maximize it, and then for sure we're safe, and we're going to have at least a bound for it. Taylor's theorem says there is a special C somewhere. You can't necessarily find it, because without actually having the actual, you won't know how far it is off, but it is in there somewhere. So there's this whole dilemma in my mind of, do we show the error bound as being like error less than, because truly that's what it is, less than or equal to, how bad it could be because of the max of the derivative, or do we use the equal to notation that, to be honest, your book has? I don't know. So that's my debate. That's why I'm not really writing all of this out as to what the error bound is doing, that it's bounding the error. So instead, we're just saying the Lagrange form of the remainder. The Lagrange form of the remainder of 2.3, or using 2.3 is equal to. I don't know if I like that equal to. I might change that equal to. I think we need to look at AP scoring guidelines. I did Google yesterday, that's the problem.
Can we just do what you did yesterday?
Oh, do what is it, Google?
Just say bound.
Bound by or bound within?
Yeah, so we can put an equal sign on it. Just say bound and equal to.
Oh, see, yesterday I said within, and so I didn't even put that, but I could put Lagrange error bound is equal to, which I think this R might be indicating. The problem is the R is also the remainder, so I'm like, I would rather put less than or equal to. Anyway, we'll say the Lagrange for right now. That's fine. Okay, so then we can go ahead and go to the fourth derivative. Why am I putting z? Because I need to maximize it. All over 4 factorial times
X minus 2.
Except if I'm finding it at 2.3, it'd be 2.3 minus 2, all raised to the 4. Right? Give 3 decimal places. Well, wait a minute. What am I going to plug in for the fourth derivative of z?
Just use 9.
Just use 9, because 9 is the maximum value of the fourth derivative as indicated by the problem. Now, if they didn't state that, I might have to, I'm just too lazy to bend down and keep on writing. If they didn't state that, I would need to justify why I'm using 9 with a quick little statement. But since they did state it, okay, fine, cool, I'll just plug it in. And then when you guys go ahead and plug it in, you have 0.3 to the 4th times 9, all divided by 4 factorial is?
3.
Isn't that easier than going and finding the factorial?
Yeah.
Yeah, so I would think so too. Because remember, 3 factorial was 6, and 6 times 4 will be 4 factorial. Got it. 4. So, point. Oh, I think you guys answered the wrong question. I asked about 4 factorial, but you gave me the error bound, so it is what it is. Point 0, 0, 3. Boop. Wait a minute. What did they tell me to answer?
To bounce.
Said use this. Oh, struggle. That's not the correct answer. The correct answer is going to be negative 0.003 and 0.003. Struggle.
I think you should add the values of forms of bounce.
Oh, for f of. My bad. I was thinking the error or the remainder. Thanks, Lorenzo. They said the function. How we doing?
No, you blow on Kevin. You blow on Kevin.
Oh dear. Okay, so what happens when I? Well, forget it. I'm just gonna do this. Wait. Wait. What am I adding and subtracting 0.003 from? And it says the approximation that's up above, and that's the approximation that we found with 3 decimal places. So it's okay to use a rounded answer. They're explicitly telling us to. Sorry. So yeah. So then it'd be 6.918. True. And 6.924. So then, how are we supposed to answer the one down here?
Yes. No, it's not in the bound.
No, because it's not within the
Bound.
interval formed using the Lagrange error bound. Don't say within the bound, because the bound is technically just the error possibility. Not within the interval found by the Lagrange error bound. So I'm going to say nope. And what I just said. Okay. How are we doing?
We're living.
You're living? Okay. As you guys are living, I mean, that's good. I'm glad you're not dying. Although I guess it depends on how you look at it. But it's okay. Still love you. Okay. Calm themselves. I have a whole big old collection over here of all sorts of stuff dealing with AP FRQs, past AP FRQs, and the Lagrange error bound. Okay? So, let's go find something different and interesting that we haven't necessarily seen before. I don't want to show you like all the answers per se. I'll have you play with it. Just play with one more, and then we'll look at homework and see if you've started where you've gotten stuck, and if you haven't started where you might get stuck. Yeah? This one, guys, this doesn't even use Lagrange. I mean, this is actually a really fun one with Maclaurin's, because it talks about derivatives of, but anyway, whenever it says rational function, that's fun. This one, I don't see a Lagrange, because I see a geoseries. That's not very fun. It talks about convergence, though. That'd be good review. This one, I see a few different derivatives, but I don't see a Lagrange. This one, absolute value, alternating, wait, less than 1 over 200. Oh, this could be Lagrange, except, what kind of series is this? Oh, so I could just use the alternating estimation remainder theorem. Let's see what they use. Do they use Lagrange, or do they? Oh, yeah. All right, that's no fun. That's alternating series. This one, oh my goodness, we already did this one. Go team, we're smart. That was from 2011. Let's keep going. Ooh, there was another one in 2011. Oh, it was a different form. But this one, it has an integral in it, and it has a Maclaurin, an interval of convergence. You guys don't necessarily know how to do that so well. Ooh, but it's an alternating. If it's alternating, I don't think they're using Lagrange. I think they're using, yeah, that's no fun. Okay, so moving on. How about this guy? Less than 1 over 6 factorial. Maybe. Ooh, it's a piecewise 2. Oh, that sounds fun. Let's do this one. 2010 question 6. This one sounds fun. 2010 question 6. I'll double check. Maybe it's not exactly the one I want, but I think it is. There we go. Let's freeze. It's alternating though. I guess that's not so much fun anymore. I'm seeing if I can find a better one. Give me a sec. It's alternating. Still not bad. It's just not Lagrange. Ooh, I like this one. Never mind. Change my mind. Change my mind. Change my mind. Just kidding. Just kidding. You just need to give me one more second. I'm so sorry. Just kidding. 2008 number 3. Haha. They love giving you tables of random stuff. Alright. Just kidding. This is for sure. For sure? Well, look at letter C. It says use the Lagrange error bound. Perfect. Let's go. The other one was alternating, so we could have just used the alternating estimation. I feel like I keep on changing that name every time I say it, but that's okay, right?
What? That's fine. The hawk.
No, that's twin. Or I mean triplet. Or I mean, I don't know.
They're still twins. Just I was AJ. Me and AJ make up one person too.
Okay, shh.
Got work, Abby. Those are mine.
Oh, there you are.
Oh, 'cause I left one in there.
Oh. Man, we came in a little fist today. I shared your complaint, your request to Melanie. Like, David respectfully requests more marking.
I'm pretty sure that one.
It's question 3. Oh, but it's 2008.
Make sure there's no dark chocolate now.
No. 2008, when did they make the switch there? I think it's a calculator question. Oh, I can look at, well, don't just go off of that. Don't just go off of that. But yeah, I think it's a calculator question. Yeah, there are decimals. It's a calculator question. This was before they made the switch. It used to be questions 1 through 3 calculator, 4 through 6 none. But then they changed it to 1 and 2 calculator and 3 through 6 none. Remember, they're giving you way more than you need. Focus.
Please do.
They're right in front of the audience. 4 boys, 2 girls. Although I think the 2 girls are probably going to 4 boys. Someone's doing the robot, but in a weird, disturbing way. Now this little, shut up, thing going on. It's a little Everest. It's a little Everest. Everest's little brother, and it's Alex's little brother, and it's I don't know, other little brothers probably. Not sure that one. Chinchilla? A little chinchilla?
Like the
Yeah.
right.
Jason Chinchilla. Jason Chinchilla's little brother. Those little brothers. They'll grow up one of these days.
I actually think I know what I'm doing.
Maybe.
Surprise.
Yeah, if we're lucky. The good thing they have big brothers to look up to, Simone. Hopefully.
I don't know any other class.
My brother called me a waste of space.
Johnny crying. Think of the formula. Think of the formula, right? Guys, come on. Whenever you see an FRQ, you have to think of the formula. When it says Taylor polynomial, you think, okay, of who? H. All right. Centered about what? 2. Cool.
Yes.
H of 2 plus H prime of 2 times X minus 2, right? Isn't that the same thing as a tangent line? First order Taylor polynomial is just the tangent line.
Isn't it? It's negative 0.1?
But not 9.
Isn't it?
Use it to approximate. Plug in 1.9 AJ, and when you subtract, it will give you negative
1.9
in the x.
Minus 2.
Is this approximation greater than or less than? I think you have to think about concavity, because the first order Taylor polynomial is a tangent line. And tangent lines are either above concave down or below on concave up.
What is
Yeah, always on.
Oh, yeah.
I'm going to show A in just a second for you guys to be able to grade with. A first order Taylor polynomial is a line. Nope, don't think about that. Nope, don't think about that. You're in a table. You're in a table. You have to think about what's given in the table, not make assumptions about what's on one side or the other. So don't look at H prime. How do you know it's less than? Oh. No. No.
That's what I was doing. Looking at the H of 2.
Oh. No. Because the table, you don't know what's going on one side or the other. All you know is what's at.
Yeah, it could be like 2.
Yeah. So H I don't know. H prime I don't know. I can't look on either side. But H double prime I know at. What's H double prime tell me? At 2.
488.
Oh, but what does that tell me? H double prime being that positive number tells me what? H double prime being positive. And a first order is a tangent line. What are all tangent lines to concave up pieces? Below or above? It's an under above.
So it's less than. So my guess is right. But like
Your justification sucks.
Oh, okay. We just had the wrong reasoning. Well, I would have gone.
Because if the concavity was down, but it wouldn't have gotten equal.
Half credit.
Part C is so interesting.
Okay. B.
What is?
Part
Part C.
C.
Oh, yeah.
I should have thought.
Part A, here's the answer. You guys can grade it.
Oh.
It was worth 4 points? What? 4 points? Now remember, if you put something illegal, even if it was something light, even if you got the right final answer, you still would have lost some of the 4 points that you would have earned. Meaning, if you put an H and a P and you put equals, or if you put H and equals and not approximate, there went one of your points, even if it wasn't one of the expressly given points. H needs to be approximate to if you put HF. Maybe you didn't. Maybe you didn't. What if you rewrote this wrong and put 127? Well, there went another point. Well, I guess we lost that. Sorry, Janelle, what?
If you didn't write the H.
Then you're okay. You could have used the words less than, or you could have used under, or you could have used lower than, right? Now hold on, wait a minute. They put since H prime is increasing. Now careful. Even if you see it, even if you got the less than, but you didn't get the reason, you didn't get any of those points. Because there was only worth 1. Now, hold on. The less than, with the reason, is there any other way of describing it besides saying H prime is increasing? You can also say just H double prime is positive, right? You can say H double prime is positive. That's another way of saying H prime is increasing. Can you say H double prime is increasing? No. Can you say H is increasing? No. You can say H double prime is positive or H prime is increasing. Say it one more time. What function? The derivative function? The second derivative function? If you say h, then yes. If you just say the function, that makes sense. Careful. So h is concave up, h double prime is positive, or h prime is increasing. Now think about that, guys. If h double prime is positive, if h double prime is positive, that means h prime is increasing, which means the rate is getting faster at higher. The rate is increasing. How else do you say that? That h prime is positive. That h is increasing faster, and if h is increasing faster, if you used a line to approximate, you went up on the line, but the rates increased in between. So the concavity, remember, is telling us about the rates getting higher at a faster rate, or I should say h getting higher at a faster rate, which means that curvature is up, which means that tangent line, while good and while showing an increase, is not going to be as much of an increase as the actual. Anyway, there are ways of trying to tie together the concepts that you don't get far behind. Question, how many points is every FRQ added? 9. Oh dear, we haven't done very many of these. Every FRQ is worth 9 points. Almost half of them were in number 1, letter A. That's rare. Usually letter A has like 1 or 2. Letter B. Did you guys write the third degree Taylor polynomial about x equals 2 and use it to approximate 1.9? You plug in your h of 2, your h prime of 2. You already had that one. You just had to go 1 or 2 more, right? H double prime of 2. Ooh, did you do over 2 factorial? And then h triple prime over 3 factorial? Nope, check it. Check it. It was over a 3, and you needed the 3 to be over a 2 factorial. 3 times 2 times 1 is 6. Over a 3 times a 3 factorial will be 3 times 2 times 1, which is 6 times 3 is 18. You had to take your h double prime, your h triple prime, and put it into your formula, which had an additional 2 factorial, 3 factorial. Now question, did you have to make it 6 and 18? Heck no. Couldn't you just put it over 2 factorial? 488 all over 3? Or 448 all over 3? All over 3 factorial? I'm messing up my factorial, sorry guys. You didn't have to write that though, because remember, some of you, to be honest, would have probably made a mistake in putting those two denominators together. You don't have to write it, just write like the actual form of it. You don't have to simplify. But did you have to plug in? Yes. Did you have to show the plugging in? No. What if you write the plugging in wrong? They can take away one of your points. Stop. Just plug it in your calculator and say dun 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 dun.
Oh, so we don't have to say, we can just put that in.
But you had to write out the polynomial because they stated it, right?
Oh, yeah.
But you didn't have to make it all nice and simple and neat. You just had to write it out.
So you don't have to write the h in 1.9.
Right. However, showing the understanding of the question is usually proper to say like, hey, I'm approximating h of 1.9, so you're kind of just stating a nice full sentence in answer to their question. But you didn't have to put that piece of 3 of 1.9 necessarily. You could have just done here and here.
Oh, and then we don't put the equation, we just put the approximate?
Because it's approximated. Okay, letter C is a bit interesting. Letter C says, use the Lagrange error bound to show that the third degree. Okay, third degree, well, I'm going to the fourth, right? The third degree approximates h of 1.9 with error less than 3 times 10 to the negative fourth. Guys, at the end of the day, you just want to be able to write less than 3 times 10 to the negative fourth, exactly like they stated. You want to be able to write that and have something that truly is less than. But here's the dealio. Ready? Ooh, and hey, look at how the AP writes it, because this is part of how I want to maybe change the Lagrange part. They are like, okay, we need to talk about the fourth derivative. So talking about the fourth derivative, we could find that from up above in the in the table, right? Yeah. So the fourth derivative, and we're doing it specifically at 2, right? Yeah. So I can steal 584 over 9. Well, hold on. I'm not supposed to steal the fourth derivative at 2 unless I'm doing an alternating series something, so I'm just going to the next term, or unless I know that's the maximum, the highest it could possibly be. How do I know that that's the highest it could be on, wait, what interval am I supposed to be looking at? I'm supposed to be looking at 1.9 to 2, right? I'm supposed to be thinking about z within 1.9 to 2. Why is the Lenzo talking about how h quadruple prime is increasing? He has to justify. You had to justify why you were allowed to use 584/9. Lagrange says it needs the maximum value of the fourth derivative on the interval 1.9 to 2. If the fourth derivative is strictly increasing, where is it going to be the highest? At 2. What am I allowed to use it to? But you had to justify, or else you are not showing full comprehension and full application of Lagrange. So then, checking out the question, does this say justify? No. But what did you have to do to show full understanding? You had to justify, or else you were not. Either you were not allowed to plug it in, or a better way of saying it is you would not have connected and made a full solution to why you were plugging it in. Do you see how they gave you a point for reasoning, but they didn't ask for a justification or an explanation? This is a struggle. They need you to have a seamless solution, and part of that seamless solution is having a basis or a foundation or a display of full comprehension as to what you're using and why you're using it. Doesn't mean we have to start defining, well, Lagrange is this guy who, no, okay, we don't have to do that. But we do have to say, wait a minute, we needed the max of the fourth derivative. The max of the fourth derivative, wait, why is it that number that I can steal? Oh, because the fourth derivative is increasing, so therefore, to be honest, I would have even been more precise than this, right? I would have done 1.9 to 2. I didn't need to even do to 3, but whatever, that's fine. So we can go ahead and plug and chug back to the Lagrange error bound. Now check it. How is the AP showing the Lagrange error bound? So we're going to go ahead and change how we show it. That way we don't have to worry about it. Well, they put an equal sign for what this equals. In succession, it would have been equals here, and then it would have been less than that. You see it? So it was the error, the remainder is less than or equal to the Lagrange error bound, which the Lagrange error bound is equal to, which is less than. Now here's the crazy part. Ready? You did not have to write that, because what if you plugged it in wrong? All you need to do is, I did it right, so it must be. And if you want, you could go ahead and plug it in your calculator and make sure. But you do not need to write that decimal, because what if you round it wrong? What if you put it wrong? What if you plug it in wrong? Just write it and be like, true. And sometimes, if you can't use a calculator, you're going to be writing something that you're not sure is true, but you sure hope so, because you think you did it right.
That's it. If you got like you got 2.6 something, like you just messed up.
You lost one of your points. Because if there's anything incorrect in your solution, we have to take away. Even if you get a final, like, even if this is right, which is less than, but if you wrote that wrong, maybe not both, but you would lose. Is it okay? Do you get the whole, like, to some degree there was a justification necessary even if it wasn't explicitly asked for in the beginning? Careful. We're going to fight for every point that we can, yeah? Because we're going to make mistakes. We know we're going to make mistakes, but on the ones that we can understand, we need to make sure our solution is perfect. But to that end, guys, let's get back into our notes real fast. And let's go back to that Lagrange, because I need to change that. I just needed a reason to, but now I have a reason to. I want to go ahead and wipe this out. Let's do this. Let's do this. Sorry, here we go. Let's do this. We're going to change this to B. You guys should know by now it's the remainder. You should know by now that it is also known as the error. Let me move this just a little bit. Okay. So we can say the remainder, which is equal to the absolute value of the nth degree Taylor polynomial minus the actual is bound by the Lagrange error bound. We're going to change that in our card. Okay? If the AP does it that way, we're going to do it that way too. And once again, I think the equals is coming from the Taylor theorem that says there is some special x equals c within the interval where it's going to be perfect, because we don't know what that is. So we have to think of the maximum as our worst case scenario. Does that kind of make sense? Sorry, I took a little longer on that than I wanted, but I did get to figure out how I want to do this Lagrange error bound endeavor card. I heard my name. I also have homework open for us to peek at if there's any place that someone has already gotten in and gotten stuck that you want to talk about. But first of all, what was the question I missed, AJ?
So on the exam
Yes.
example, it says that it was over 4 factorial. Over 4 factorial.
Oh, here. Yes.
Um,
You could have written that over 4 factorial this direction.
But didn't on the card it says n plus 1, so wouldn't it be?
But careful. N was what degree Taylor polynomial we were using to approximate, which was the 3rd degree.
Oh.
So n is 3, n plus 1 became 4. Does that make sense?
Oh.
Yeah. So the 4, I mean, we just kind of went there. We didn't really talk about the n plus 1, but yeah, this was a 3rd degree Taylor polynomial approximation. So then Lagrange says look to the 4th derivative, the 4th factorial, and the 4th power. Good question. Good question. Anything else? Sorry, before I transition away from the FRQ scoring guideline? Okay, cool. So I'm in homework. Anybody have a particular, oh, hi, webcam that's not working. Oh, well, I'm looking at the homework. Is there any place that you guys have gotten stuck that you want to talk about? Yeah? Homework starts off with, ready? Listen. Homework starts off with, use the special table of Maclaurin series. Isn't that endeavor number 27?
Yeah.
Oh, cool. Oh, we get to just play with those? That's fun. Use the remainder bounding theorem. The remainder bound, oh, I skipped those ones. Never mind, don't do that. Just kidding. Use the alternating series error bound. If you have an alternating series, we can just say the error is less than what? Or the error is within what? Alternating series. It's within the next term, right? And Lagrange is within the n plus first derivative. N plus first derivative maximized over the n plus first factorial times x minus c to the n plus first. Okay. There is going to be one thing that's going to be a little interesting for you guys to face. But we'll just talk about that in number 19 when you guys come in tomorrow. Number 27, Monday. Pause. Wait a minute. If it says find the linearization of something, what's the linearization referring to? Tangent line. What's another word for tangent line that we just saw in the FRQ? First order Taylor polynomial. Oh well, that was fun. Anyway, so linearization, yes, it's a tangent line, but remember it's also the first order Taylor polynomial. But when it says, the quadratic approximation, you're doing the second order Taylor polynomial. It's another way of saying the second order Taylor polynomial. That's fun. So could the 3rd degree Taylor polynomial be a cubic approximation? Anyway. That's like a long answer-ish. You guys have seen plenty of ones like that. That's a differential equation problem having to do with power series. That's fun. And then you have multiple choice, and you're done. Boom. All right, cool kids. What are we doing when we come back on Monday? Well, if we had a little bit more time, we would do it today. But sadly, we kind of don't.
How many sections are in each of those things?
Oh, that's a great question. We can go look at it. How close are we to the end of notes? Ooh, there's a quick quiz, but don't worry. That's what we're going to do on Monday, first thing when we get in. But then we have 2 more sections.
What's next?
The next section is going to be, those are series. The next. Hey, wait a minute. Are the 2 sections combined into one?
Yeah.
Yeah, but then there's more.
Nice one.
Oh, I saw.
Oh.
Yeah, only one more homework, but 2 sections in that one homework. Wait a minute. How on earth can she be doing 2 sections? Do you guys see it? In 1, 2, 3, 4 slides.
Because we learned that in chapter 9 OT.
Because this book is teaching all of the convergence and divergence tests in 2 sections. Our book, the other book, took a whole chapter 9. Now wait a minute, didn't this book already kind of do geometric? Okay, it already kind of did geometric. And it already kind of did the divergence test. But all the other ones, wait. All the other ones just get introduced as a way of solving for an interval and radius of convergence? Our book decides to be like, we don't really care until we have to do this. So, we've already done the convergence and divergence, but that also means for the chapter 10 test, we have to know all of chapter 9 and chapter 10. That's okay, that's like all basic calculus, right? You gotta know what comes before to be able to do what you're doing now, to be able to go forward.
So they're just using the ratio.
So anyway, we have to figure out an interval of convergence by basically doing what's similar to a ratio test-ish, but with x's and a's. And then we have to test the convergence at the endpoints, and we're going to test the convergence at the endpoints by basically doing all of our parting C. Well, not all of it, but choosing an appropriate one. To find the interval of convergence for anything other than a geoseries. We've been building up to this since the very beginning because we were like, interval of convergence, geo, got it, absolute value of R less than 1. Anything non-geo, is it on in Endeavor 27? Otherwise, we don't know.
We forgot to pass out the test.
Oh, I forgot to pass out the test. Go get correction papers.
No.
Thank you, Lorenzo.